In this lecture, we're going to give an introduction to the last topic of the course, which is ordinary differential equations. So, a differential equation is an equation that involves a derivative or derivatives of an unknown function. For example, the first example shows a relationship between the derivative of y with respect to x and y itself. The second example shows a relationship between the second derivative of y with respect to x, the third derivative of y with respect to x, and x and y. The last example shows the relationship between the second derivative of a function t, whose arguments are x, y, and t. So the second derivative of t with respect to x plus the second derivative of t with respect to y is equal to a constant multiplied by the first derivative of t with respect to the argument t. We are going to discuss the types of differential equations at the end of this lecture, but just as an introduction, we have ordinary differential equations and partial differential equations. Ordinary differential equations, we have in them an unknown function which depends on a single variable. Y is a function of x, and usually I'm trying to find y knowing a relationship between y and its derivatives and x. A partial differential equation, on the other hand, is an equation that involves an unknown function y that's function of more than one variable, and the equation involves y and its partial derivatives with respect to the unknown variables. Motivation. Why would we want to study this? To predict the future. This has always been the objective of all our models, all our differential equations. If we know some relationships now, can we predict what's going to happen in the future? Many engineering fields involve models, and the models involve prediction of certain phenomenon, what's going to happen when I apply certain loads, what's going to happen when I do some sort of any engineering activity. I'd like to know the effect in the future on different variables. For example, in mechanics, we're usually concerned with what are the stresses when the loads change. Here are some examples that differential equations can help to solve. In engineering, is a bridge stable against breaking? Environmental sciences. How rapidly does a waste product from a chemical plant invade the water table? So by knowing a relationship between the speed of motion of the product, of the concentration of a product, as a function of other variables, we can know the accumulation of waste in lakes. Of course, we've all heard about the current situation of the COVID-19. So there are models to predict how fast does a disease, or does this disease, spread in a population, and so on and so forth. Many examples in engineering, in biology, in economics, that rely on solving differential equations. A few years ago, you guys probably were still in high school, or even before that, there was a very nice movie. It's called The Martian, where a person was stranded on Mars, and the only way that this person could leave Mars was, as of course per the plot of the movie, was if they were going to send a spaceship, and that person had to in another ship had to meet that particular spaceship at a particular point, so that that big spaceship can return that person back to Earth. And the movie talks about certain trajectories of those spaceships as they move in space, and whether they're able to meet at the same location or not. And in order to predict something like this, that involves solving differential equations that discuss the relationship between position and time due to forces applied on different particles. So we're going to go through a particular example. For example, that example discusses the Newton's second law of motion that says the mass multiplied by the acceleration is equal to the force applied. So given a particle, the acceleration of this particle is depends on the force applied on this particle. If we apply this Newton's law of motion on a particle with mass m under the gravity load and with a spring force F, the differential equation becomes mass multiplied by the acceleration, which is the second derivative of the position, is equal to the forces acting on the particle. The forces are the gravity force minus kx, which is the force in the spring. This is an easy differential equation that we can solve, and the solution for this equation is given in front of you. The the position is equal to mg over k plus a constant multiplied by cosine term function of t plus another constant multiplied by the sine of some constants, some parameters as a function, and t. And so this what this predicts is, depending on the initial conditions, this mass will be oscillating around a particular position. If we assume that the initial position is 0, the initial velocity is 0, then the position of that mass will follow this equation that you have right here. I've also here provided some mathematical code that you can copy and paste, and you can change the parameters of the problem and see the effect on the dynamic behavior of that mass. You can also add damping to the equation. So damping is usually involved or added by a term that's directly proportional to the velocity. This equation says that the force acting on one of the forces acting on the mass is equal to negative a constant multiplied by the velocity, which basically says it's the higher the velocity, the higher the damping. And right here we provide some possible solutions given the initial parameter, given the parameters m, k, and b. And here there is some code. If you use that code and if you copy this code and paste it into Mathematica, you'll get the previous solutions. Another example in mechanics is the Euler-Bernoulli beam, and we are going to study this beam in more details in CivE 398. In this beam, we relate the fourth derivative of the displacement of the beam to the applied load Q. Given certain conditions for a distributed load, the displacement, an exact solution to this differential equation can be found here, and you can find more details on the specific boundary conditions in your online notes. Growth and decay are usually modeled by relating a particular speed to the actual population. So for example, you can relate the change of a particular quantity with respect to time is directly proportional to the actual quantity itself. So dx by dt is equal to k multiplied by x. Solving this differential equation, you can find that an explicit expression for x as a function of t. The constant C1 can be obtained knowing the initial conditions. If the initial quantity when time is equal to 0 is equal to a, then the expression becomes x is equal to a multiplied by e to the power kt. Decay as well, if a quantity decreases, decreases as a function of time, and as a function of how much there is already, that is called the decay equation, and the equation is given by the speed dy by dt is equal to negative a positive constant h multiplied by the quantity itself y. Similarly, the solution to this differential equation is given by y is equal to c1 e power negative ht, and if I know the initial condition, what is the value of y when the time is equal to 0? If it's a, then the solution becomes y is equal to a multiplied by e power negative ht. I'm not going to go in details in these examples, but differential equations apply to all sorts of engineering applications, even electrical engineering, which the relationships between the voltage drop, the current, and the resistance, these are all satisfy certain differential equations. Economics, the stock, the different prices for different stocks can be modeled using differential equations, and here I point you to an article for those who are interested in learning more about how stocks are modeled using differential equations. They can read this Wikipedia article. Movies, a lot of the movies, while you might not know that, but a lot of the phenomena that you observe in movies are actually based on solving differential equations to be able to model the phenomena in these movies as realistically as possible. And here I provide you some links where you can see how differential equations were used to provide realistic movies. So you can go log onto these links and see how these were modeled. A very interesting link that I found, actually an earlier instructor to this course, Dr. Kamiar Davoudi pointed it out to me, is you can even model love affairs using differential equations. So for example, if you assume that Romeo and Juliet, they're in love, and if the rate of change of that how much Romeo loves is how much love Romeo has can be modeled using the variable r. How much love Juliet has can be modeled using the variable j. And if you think that if Romeo's every time Juliet loves him, he does not love her back, so this, or the rate of change of Romeo's love is negatively affected by the love of Juliet. On the other hand, if Juliet's love is directly proportional to how much Romeo loves her, you can model this and then get a trend similar to this. If both start at a particular level of love, the same level, because they both love each other, Romeo is predicted to decrease in love. Juliet will first increase, and then her love will decrease, and so on. And then you're going to go on to this on and off relationship for an extended period of time. You can also play around with different models for this differential equation. This is a relationship between Romeo's love, the rate of Romeo's love, and Romeo and Juliet, and the rate of Juliet's love. So you can play around with these and see how this affects the final, how this reflects in the changes in the quantity r and j over time. And here's some code that you can copy and paste into Mathematica to see the effect. So we're going to talk now about the classification of ordinary differential equations, which is the subject of this course. The order of an ordinary differential equation is the order of the highest derivative appearing in the equation. This equation, for example, relates the second derivative of x with respect to t, relates it with the forces applied. So this is a second order differential equation, ordinary differential equation. This beam equation that we introduced earlier relates the fourth derivative of y with respect to x4 to the distributed load q. This is a fourth order ordinary differential equation. An ordinary differential equation is considered linear if the dependent function that we're trying to find, which is y, and its derivatives appear linearly in the equation. So for example, the equation that you see here, the nth derivative of y with respect to x power n and all the other derivatives and y itself appear linearly. They are not multiplied by each other. If the dependent function, which for example in this case is x, if itself or one of its derivatives appear non-linearly in the equation, then it's called a nonlinear ordinary differential equation. So for example, dx by dt is equal to k over x, because x is the dependent function, it depends on t, and x appears in a nonlinear fashion. This is the nonlinear equation. Similarly, the second derivative of x with respect to t squared is equal to sine x. This is a nonlinear differential equation. We're going to also categorize differential equations, linear differential equations, as either homogeneous or non-homogeneous. So if a linear or ordinary differential equation is considered homogeneous if every term has y, which is the dependent function, and its derivatives. If, on the other hand, one term does not have y and its derivative, y or its derivatives, then it becomes a non-homogeneous ordinary differential equation. And again, we're discussing only linear differential equations. So as an example, when we considered the Newton's equation of equilibrium applied to a mass, there were two versions of it. The first version was, m, the second derivative of x with respect to t squared, is equal to negative kx, or m d2x by dt squared is equal to mg minus kx. This is considered homogeneous, while this is considered non-homogeneous. The non-homogeneous equation would have a particular term called the source term in the solution, and this would be added to the solution given for the homogeneous differential equation. Finally, the last classification depends on the boundary conditions. An ordinary differential equation whose boundary conditions are given at the initial values for the independent parameter is called an initial value problem. A boundary value problem is a problem where the boundary conditions are given at different values for the independent parameter. Usually, initial value problem is deals with equations that is function of time, and I know the values of the I know the initial conditions for the function that I'm trying to find. So this becomes an initial value problem. A boundary value problem is usually involved with finding a particular distribution of something in space, knowing the value of the function at different points within the space.